Hello everyone, welcome back to the channel. Today I'm here with a single phase half wave controlled rectifier with an LE load, inductor and a back EMF or battery connected DC battery connected to the rectifier circuit. So firstly, if I explain the model, I have a source volt AC voltage source connected to the thyristor. The thyristor is triggered on and off using a pulse generator, and it is connected to the inductive load of 50 microhenry. Then a battery of lithium ion battery of a nominal voltage 100 volt and initial state of 100%. Then I am giving a standard single phase voltage of 230 volt, and I am calculating the peak voltage from phase voltage by multiplying the phase voltage with root 2, and I get a peak voltage of 325.3 volts. That peak voltage is used here at the peak amplitude 325 volt. That means our AC sine wave will swing from peak of 325 to negative 325. Next, to turn on and turn off the thyristor, I am using a pulse generator, and these subsystems will calculate a pulse delay and a period. Considering the alpha or firing angle of 90 degree, I have a subsystems that will first calculate the period. When I do 1 divided by frequency, I'll get a period of, and since my frequency is 50, I'm using my frequency 50, and I get a period here. Period divided by 360. Why 360? For sinusoidal wave, a full cycle is 2 pi, and it is equivalent to 360. So period time divided by 360 will give me a value here, and when I multiply that value with the firing angle, I'm going to get pulse delay. So at a 90 degree angle, I'm getting a pulse delay of 0.005 and period of 0.02, which I will use here. My period of 0.02, amplitude 1, and phase delay of 0.005. That means I am going to turn on my thyristor or rectifier at the angle of 90 degree. I have voltage measurement block to measure the source voltage here, which is Vs. I have VTH, which will measure the voltage across the thyristor, and Vload will measure a voltage across the load. And Vload is given to the mean to find the average DC voltage, and current measurement block is used to measure the IDC, and it is given to the mean to find the average DC current. Signal from all of this were given to the scope, and let's run. Okay, now you can see that my nominal current is 100. So with the capacity, I am almost getting 119 volt. My IDC is 119 volt, and I am also getting an average DC current of 119. That is the effect of having a battery. Effect number 1 of having a battery, or this back EMF. In case of a motor, it represents the armature. Then in this circuit, let's go to the waveform first and explain. Too much. Okay. From here, this first panel is showing us a source voltage. This one is showing the pulse generator. This one is showing the voltage across the load. Then this is showing a IDC, and this one is a thyristor voltage across the thyristor. What happens? The sinusoidal wave from here to here, half wave, first positive half wave, from here to here is negative second negative half wave. So positive half wave and negative half wave makes one period, 2 cycles, 1 period, and when we reach here it is 2 pi or 360, and when we convert into the time it is 0.02. Here it's pi, and when we reach here it's 90. So 90 degree at the 90 degree, or pi divided by 2, and the time period is 0.005. The thyristor initially, is reverse biased, and it's not conducting from 0 to 90 degree, or 0.05 seconds, 0.005 seconds, it is not conducting. Hence, at the voltage, at the load side, we do not see any voltage, and no current is flowing until at the 90 degree angle. Once it hits the 90 degree angle, the pulse generator will generate the pulse and triggers the pulse, and after a few seconds, with a certain delay, after a few seconds, the thyristor turns on and it starts conducting. Therefore, we can see a voltage across the load, and current is also gradually ramping up. We do not see a step current. The current is gradually ramping up because of the inductor load. And when we reach at the negative half cycle, 1 epsilon after that, because of our inductive load, we still have a current here around 19 amps, and the thyristor cannot block the current immediately, and therefore we experience the negative voltage, and the thyristor is still conducting until the current gets to 0. So from here to here, it the thyristor is conducting and forward biased until the current is 0. Once the current is 0, then the thyristor is reverse biased, and it blocks the current until next pulse is triggered. So that will be repeating all along, and the voltage across the thyristor is since the initially voltage initially the thyristor is reverse biased and it's not conducting, it have some voltage. Once it starts conducting, the voltage across the uh, thyristor is 0, and again when it is reverse biased it experiences a negative voltage. Then till it starts ramping up at the positive half cycle, it experiences positive voltage. Again it starts conducting, therefore its voltage is 0, and it repeats. Now you have seen the effect of inductor and one effect of uh, having a back EMF. So when you can see that our back EMF voltage is around 119 volt, which is, do we have 100 nominal voltage multiplied by our rated capacity of a voltage battery, we have nominal voltage, the voltage of 119, and we also get an average VDC of 119. So when the thyristor fires at a 90-degree angle, the current won't immediately flows just because the gate pulse arrives. The AC source has to rise. This AC source has to rise above the back EMF before conducting, before conduction can actually begin. So in practice, the effective start of conduction is slightly delayed compared to the angle of 90 degree. So for instance, we have 119, the source is 230, so the real current will begin only when the source voltage exceeds the 119, and over the cycle the inductor keeps the keeps the current smooth, right? And because it has to balance its stored and released energy, so from here it stores, then it starts releasing smoothly. The average load voltage ends up very close, so the average load voltage will ends up close to the VT voltage. Now next effect is, if we start if the ED is more than the source voltage, our source voltage is 230, if we say 250.
I think it will be better for you to sleep now, Jacho.
Let's run. Now you can see that though we have an average voltage, DC voltage near to this one, the current is very small, and you can see that um, as soon as the voltage drops below the uh, ED, the current starts decaying. Look, initially there is the voltage is high. However, as soon as it starts decreasing and it is less than the when the uh, source drop below the ED, then the current starts decaying and it stretches something like this and becomes a current very low, very small current. And you can see that even the conduction period of the thyristor is small. ED opposes the source and overall current magnitude is reduced, and it behaves like a motor. uh, this same principle is used in a motor speed control where when the ED rises up, then the less current flows and the power drawn from the rectifier decreases. If the motor slows down, then ED drops, more current is pulled, and the rectifier delivers more power. This dynamic is exactly what happens, what makes a controlled rectifier useful in a motor speed controller. Okay, that's all for today. I think I have covered everything, and I will make this file available for you to download it. You can check my bio. I have a link in the bio. Uh, thank you for watching. See you next time.